Dear students, welcome to the PowerPoint presentation of Physics for Class 12. In this session, we will summarize about electrostatic potential and we will also solve worked examples in the end. Welcome once again. Please listen to this lecture carefully as it will help you in your examinations. Summary. Electrostatic force is a conservative force, work done by an external force, which is equal and opposite to the electrostatic force in bringing a charge from point R to point P is given by Vp minus Vr. This is the potential energy of the charge between final and initial points. Potential is the work done per unit charge by an external agency in bringing a charge from infinity to that point. Potential difference between 2 points is physically significant. Please note the difference between potential and potential difference. Potential is the work done in bringing a charge from infinity to the point, whereas potential difference is between 2 points. If potential at infinity is chosen to be 0, potential at a point with position vector due to a point charge q placed at origin is given by V equals 1 over 4 pi epsilon naught into q by r. Potential due to a dipole moment at P placed at origin is given by V equals 1 over 4 pi epsilon naught P into R divided by R square. Here P is the dipole moment, R is a unit vector in the direction from that point to the origin, and R square is the distance of the dipole moment. For a charge configuration Q1, Q2, Q3 etc. up to Qn with position vectors R1, R2 up to Rn, the potential at point P is given by superposition principle, which says V is equal to 1 over 4 pi epsilon naught open the bracket Q1 by R1P plus Q2 by R2P plus etc. up to Qn by Rnp close the bracket. Here R1P is the distance of point 1 from the point P. Equipotential surface is the surface at which potential at all points is same. The points on equipotential surface have the same electric potential. The work done across any 2 points on equipotential surface is 0. The electric field E is always normal to the equipotential surface. The intensity of electric field along equipotential surface is always 0. For a point charge, concentric spheres centered at the location of charge are equipotential surfaces. Let us summarize once again these points. Equipotential surface is the surface where potential at all points is same. That is, V is same all around the equipotential points. They have the same electric potential. The work done across 2 points on equipotential surface is 0 because V is constant. The electric field E is always normal to equipotential surface. So if you draw a normal at a point on equipotential, it represents electric field. The intensity of electric field along the equipotential surface is always 0. So here the intensity is also 0. For a point charge, concentric spheres centered at a location of charge are equipotential surfaces. Suppose a charge is located at the center, its equipotential surface is represented by a concentric sphere. Potential energy. Potential energy stored in a system is the work done in assembling charges at their locations. It is represented by U, the letter U, capital U, and that is equal to the work done. Work done in bringing those charges from infinity to the point of location, or bringing a system external by a external agency. That is U is equal to W equals 1 over 4 pi epsilon naught Q1 Q2 divided by R12. Here R12 is the distance between two charges Q1 and Q2. Having studied about the potential difference and equipotential surfaces, let us study about capacitors. A capacitor is a system of two conductors separated by an insulating material. Its capacitance is defined by term C is equal to Q divided by V, where C is the capacitance, Q is the charge, and V is the potential difference between two conductors. Capacitance is determined purely geometrically by shapes, size, and relative position of the two conductors. You see here, this is only the geometrical shape, and it is not depending on any other thing. Capacitance of the material is purely geometrically determined by shape, size, and relative positions of the two conductors. The SI unit of capacitance is farad. 1 farad is equal to 1 coulomb per volt. For a parallel plate capacitor, the value of capacitance is given by C is equal to epsilon naught into A by D, where C is the capacitance, epsilon naught is the permittivity of vacuum, and A is the cross section area of the plates, and D is the distance between the two plates. Dielectrics and polarization. Dielectric develops a net dipole moment in presence of an external electric field. Dielectric is a material like mica, plastic, paper, or mineral oil, which is inserted between the two conductors of the capacitor to increase the capacitance. And when we insert this dielectric material, it develops a dipole moment in presence of an external electric field. This dipole moment is called polarization. So, the dipole moment per unit volume is called polarization, and it is denoted by a letter capital P. Hence, the dielectric material increases the capacitance by a factor K, called the dielectric constant, which is the characteristics of the material. So, as we know, when we add dielectric material, the value of K, which is greater than 1, changes the permittivity. Earlier, the permittivity of the vacuum was epsilon naught. Now, after inserting dielectric, it becomes K into epsilon naught. Correspondingly, the value of C also increases by a factor K. Hence, new capacitance, that is with dielectric, the value of capacitance will be equal to C is equal to K into C naught. Capacitors in parallel. When we connect two capacitors C1 and C2 in parallel, the capacitance equivalent capacitance is given by the formula C equivalent equals C1 plus C2. So, capacitance in parallel C equivalent will be equal to C1 plus C2. Similarly, if we connect capacitance in series, that is side by side, its reciprocal adds up. So when we connect two capacitors C1 and C2 side by side or in series, 1 over C equivalent will be equal to 1 over C1 plus 1 over C2. That can be simplified as C1 plus C2 divided by C1 C2. So capacitance in parallel add up, and in case of series capacitance in series, reciprocals add up. The energy stored in a capacitor is given by U equals CV square by 2 in terms of capacitance and potential difference. That can also be written as Q into V by 2, where Q is the charge and V is the potential difference, or it can also be written as Q square by 2C. So for solving numerical problems, we can use any of these three forms of energy stored in a capacitor. A Van de Graaff generator consists of a large spherical conducting shell. By means of a moving belt, suitable brushes, charges are continuously transferred to the shell and potential difference of the order of several million volts is built up, which can be used for accelerating charged particles, which in turn are used to break atoms. So, Van de Graaff generator is a device of a large spherical conducting shell. There is a big shell in the top and a smaller shell at the bottom. These two shells are connected by a moving belt and suitable brushes. Charges are continuously transferred to the shell from lower end to the upper end and then in turn transferred to the bigger shell. And the potential difference of the order of several million volts is built up, which is used for accelerating charged particles. With this, we come to the end of summary part. Now let us go and solve worked examples. Before that, we will revise the physical quantities. Potential difference. Potential difference V is equal to potential is represented by a symbol V. Its dimensions are ml square t to the power of minus 3 a to the power of minus 1. Its unit is volt. Normally we use the word potential difference, which is physically significant. Capacitance C. C is the symbol of capacitance and its dimensions are m to the power of minus 1, L to the power of minus 2, T to the power of minus 4, A square. Its unit is farad. Generally, farad is too large a quantity. We mention microfarad, which is equal to 10 to the power of minus 6 farad, or picofarad, which is equivalent to 10 to the power of minus 12 farads. This also, microfarad and picofarads, we are using in solving numerical problems. Polarization. Capital P is the symbol of polarization and its dimensions are L to the power of minus 2 AT and its unit is coulombs per meter square. It is nothing but a dipole moment per unit volume. So if we divide dipole moment by volume, then it is called polarization. Dielectric constant. The symbol for dielectric constant is K and it is dimensionless. Hence we conclude this and we will take up numerical examples in the next slide. Example 1. Calculate the potential at point P due to a charge of 4 into 10 to the power of minus 7 coulomb located 9 centimeters away. Hence, obtain the work done in bringing a charge of 2 into 10 to the power of minus 9 coulomb from infinity to P. This is the example for calculating the potential and the work done. The two charges are, one charge is 4 into 10 to the power of minus 7 and the test charge is 2 into 10 to the power of minus 9 coulomb. Hence, we have to calculate work done and the potential. And he has asked another question whether the answers, that is the work done and the potential, depend on the path along which the charge is brought from infinity. Solution. Given Q is equal to 4 into 10 to the power of minus 7 coulomb. And the distance r is given in centimeters, 9 centimeters away. We have to convert it into meters. So 9 divided by 100 becomes 0.09 meters. Potential. Here now we have to calculate potential using formula V is equal to K into Q by R. The value of K, though it is not given in this problem, but we have to assume it as 9 into 10 to the power of 9. So K is equal to 9 into 10 to the power of 9 into 4 into 10 to the power of minus 7, which is the charge Q, divided by 0.09. Please note it is the source charge 0.9, that is equal to 4 into 10 to the power of 4 volts. Solving, we get V is equal to 4 into 10 to the power of 4 volts. Work done. Work done is given by Q into V, that is equal to 2 into 10 to the power of minus 9 into 4 into 10 to the power of 4, that is equal to 8 into 10 to the power of minus 5 joules. Q, the value of Q is 2 into 10, this is the test charge. We are bringing this charge from infinity, so its value is to be taken 2 into 10 to the power of minus 9 into 4 into 10 to the power of 4. It becomes 8 into 10 to the power of minus 5 joules. So he has asked one question, whether the answer depends on the path along which charge is brought. The reply is, the answer is no, it does not depend on the path along which the charge is brought. So work is path independent. Now let us take up example 2. It is given a charge of 2 microcoulomb is taken from infinity to a point in electric field without changing its velocity. If the work done against the electrostatic force is 40 microjoules, what is the potential at that point? So a charge is given, charge value, which is brought from infinity to the point in electric field at a constant velocity, and work done is given, and we have to find the potential. Solution. We know V is equal to external work done per unit charge. So that is equal to minus of 40 into 10 to the power of minus 6. This factor 10 to the power of minus 6 is due to microjoules, divided by 2 into 10 to the power of minus 6. That is the value of the charge. That is equal to minus 20 volts. So the potential at that point is V is equal to minus 20 volts. Please note, we have to always put the signs of work done and Q. Here work done is against the force, hence we have to put a minus sign. Example 3. Two charges 5 into 10 to the power of minus 8 coulomb and minus 3 into 10 to the power of minus 8 coulomb are located 16 centimeters apart. At what point on the line joining the two charges is the electric potential 0? Take the potential at infinity as 0. So in this example, two charge values of two charges Q1 and Q2 are given. One is a positive charge 5 into 10 to the power of minus 8, and the second one is a negative charge minus 3 into 10 to the power of minus 8 coulomb. The distance separating them is 16 centimeters. So the distance is given in centimeters. And he has asked at what point the potential is 0. And he has also told the potential at infinity to be taken as 0. Solution. Please see the diagram. It is shown very clearly. Here there are two charges Q1 and Q2 located at point A and B. And point P is also shown. We have to find the distance between Q1 and Q2 is given as 16 centimeters, that becomes 0.16 meters. So let the point P at which the electric potential 0 be located at a distance x from Q1. That is, let us assume the distance to be x. That is the question. So we will now the distance becomes between Q1 and Q2 will be 0.16 meter, that is 16 centimeter converted into meters, and the distance between Q2 and P becomes x minus 0.16 meter. So let the point P be located at a distance x from Q1. That is, V1 plus V2 should be equal to 0. Therefore, we have to put individual formula for V1 and V2. V1 is given by KQ1 divided by x plus V2 is given by KQ2 divided by x minus 0.16. So the potential at the we have to find x at a point where potential is 0. So we will assume V1 plus V2 equals to 0. This is given and we have to find out x. So solving the previous equation, we get k into Q1 value, we have to substitute 5 into 10 to the power of minus 8 divided by x plus within brackets minus 3. This is the negative charge. Because of negative charge, we are taking minus 3 into 10 to the power of minus 8 divided by x minus 0.16 and close the bracket. That should be equal to 0 because potential has to be 0 there. Solving, we get 5 by x minus 3 divided by x minus 0.16 equal to 0. Then again simplifying, we get 5 into x minus 0.16 minus 3x equal to 0, or 2x minus 0.8 equals 0, or x is equal to 0.8. 2x is equal to 0.8 or x is equal to 0.4 meters or 40 centimeter. This point, the answer is this point where electric potential is 0 is at a distance 40 centimeters from Q1 and 24 centimeters from Q2. Let us take example 4. Here a parallel plate capacitor with air between plate has a capacitance of 8 picofarads. 1 pf is equal to 10 to the power of minus 12 farads. What will be its capacitance if the distance between the plates is reduced by half and the space between plates is filled with a substance of dielectric constant 6. So this is the problem of a parallel plate capacitor with air as a medium initial case and whose value is 8 pf. So sometimes they will not give a conversion factor from pf to farad, picofarad to farad. We have to know that 1 picofarad is equal to 10 to the power of minus 12 farads. And the question is, what will be its capacitance if the distance between plates is reduced by half? That means in the formula C is equal to epsilon naught A by D, D is reduced by half. That is, in the case D is reduced from D to D by 2. And he is also filling up the plates with a dielectric constant material. Initially it was a vacuum or air. Now it is filled with a dielectric material with a constant 6. Let us solve it. Solution: C is equal to 8 pf, that is equal to 8 into 10 to the power of minus 12 farads after conversion. We know the formula C naught is equal to epsilon naught into A by D. C naught is the capacitance in air and epsilon naught is the permittivity of air. Hence, this is also given as C naught 8 into 10 to the power of minus 12 F. Now he is reducing this distance in the above formula from D to D by 2. And he is putting epsilon, a dielectric material with epsilon r relative permittivity equals 6. That is given. Therefore, substituting in the formula, C is equal to epsilon naught epsilon r into A by D equals C is equal to, we have to find the revised new value of capacitance, epsilon naught into 6, that is the permittivity of air, permittivity of the dielectric material, sorry, into A divided by D by 2, that is equal to 12 C naught. That is the D by 2, the 2 divisive factor of D goes up and it becomes 12. Whereas all other quantities epsilon naught A by D, that is equal to C naught. So that substituting we get 12 into C naught is in the previous example 8 into 10 to the power of minus 12. So 96 picofarad is the capacitance. So by putting dielectric material and reducing the distance, the capacitance is increased from 8 picofarads to 96 picofarads. That is the outcome of this example. Let us take example 5. Here there are 3 capacitors, each of 9 picofarads. They are connected in series. That value of C1 is equal to 9 pf, C2 is equal to 9 pf and C3 is also 9 picofarad. Then he wants us to find out what is the capacitance of the combination. So here please note the capacitance are connected in series. When the capacitors are connected in series, their reciprocals add up. Then he has asked in part B, what is the potential difference across each capacitor if the combination is connected to a 120 volt supply. Here the battery voltage or supply voltage is 120 volts. V, with the value of V is 120 volts. Let us solve it. Solution: given C1 equals C2 equals C3 equals 9 picofarads. Since capacitors are connected in series, 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So since they are equal, it becomes 3 divided by 9 into 10 to the power of minus 12. That is equal to 1 divided by 3 into 10 to the power of minus 12. Therefore, 1 over C is equal to 1 over 3 into 10 to the power of minus 12. Comparing left and right side, C becomes C equals 3 into 10 to the power of minus 12 farads or 3 picofarad. Now part B. Then he is asking to find out the potential difference between each capacitor. Since capacitors are connected in series, the potential difference is divided in the ratio of their capacitance. Because capacitors all the three have equal value, the voltage will get divided by 3. See, so therefore, V1 is equal to V2 is equal to V3 because C1, C2 and C3 are having the same values. Therefore, it is 120, V is 120 divided by 3, that is equal to 40 volts. See, the voltage across or the potential difference across each capacitor is 40 volts. Example 6. In this also 3 capacitors are given, but here the values are different. In the previous example, C1 equals C2 and C3. Here it is different. C1 is 2pf, C2 is 3pf and C2 is 3pf and C3 is 4pf. They are connected in parallel. Here also there is a difference. Previously all the 3 capacitors were connected in series. Here they are connected in parallel. We are required to find out what is the capacitance of the combination. Here the combination is parallel. Determine the charge of each capacitor if the combination is connected to a 100 volt supply. So there are two parts. One is we have to find capacitance when they are connected in parallel, and we have to the charge Q we have to find out on each capacitors if they are connected to a supply of 100 volts. Let us solve it. Given C1 is equal to 2pf, that is equal to 2 into 10 to the power of minus 12 farads. C2 is equal to 3pf equal 3 into 10 to the power of minus 12 farads, and C3 is equal to 4pf, that is equal to 3 into 10 to the power of minus 12, 4 into 10 to the power of minus 12 farads. Therefore, C parallel is equal to C1 plus C2 plus C3. We can simply add the capacitance values because they are connected in parallel. So capacitance in parallel gets added up. Therefore, 2 plus 3 plus 4, that is equal to 9 picofarads. That is the answer. What is the capacitance of combination? The capacitance in combination is equal to 9pf. Part B. Part B, it is given as Q is equal to CV. We are required to calculate the charge. Charge gets distributed in the proportion to the reciprocal of capacitance. Therefore, Q equals CV. Q1 equals C1V, that is equal to C1 is 2 into 10 to the power of minus 12 into 100. Please note the charge in case of parallel is divided in proportional to the voltage. Therefore, voltage is constant. The charge gets distributed in proportion to the value of capacitance. Therefore, Q1 is equal to C1V, that is equal to 2 into 10 to the power of minus 12 into 100. That is equal to 2 into 10 to the power of minus 10 coulomb. Q2 will be equal to C2V, 3 into 10 to the power of minus 12 into 100 equal to 3 into 10 to the power of minus 10 coulombs. Q3 is equal to C3 into V, that is equal to 4 into 10 to the power of minus 12 into 100. So these are the values of the charge on the capacitors. Here two important points. The capacitance gets added up when they are connected in parallel. Therefore, the equivalent capacitance will be C1 plus C2 plus C3, that is equal to 9 picofarads. Similarly, the charge gets divided in proportion to the capacitance, the value of the capacitance. Therefore, since C1 is 2, the charge is also 2 into 10 to the power of minus 10 coulomb. Q2 also in proportion to 3 into 10 to the power of minus 10 coulomb. Q3 equals 4 into 10 to the power of minus 10 coulomb. Let us take example 7. In a parallel plate capacitor with air between plates, each plate has an area of 6 into 10 to the power of minus 3 meters square. So, here a capacitor is a parallel plate capacitor whose area is 6 into 10 to the power of minus 3 meters square, and the distance between the plates is 3 mm. Calculate the capacitance and charge on each plate if the capacitor is connected to a 100 volt supply. And we have to assume epsilon naught is equal to 9 into 10 to the power of minus 12. So, given A is equal to 6 into 10 to the power of minus 3 meters square, D is equal to 3 mm, that is equal to 3 into 10 to the power of minus 3 meters. C is given by the formula C is equal to epsilon naught into A by D, that is equal to 9 into 10 to the power of minus 12, value of epsilon naught, into 6 into 10 to the power of minus 3, that is the area of the plate, divided by the distance separating 3 mm, that is 3 into 10 to the power of minus 3 meters. So, solving, the value of capacitance is 18 pf. Now, we have to calculate the charge. Charge is given by Q equals C into V. V applied voltage given as 100 volts. Therefore, C is, we have calculated or we have found the result in the previous line, 18 pf, 18 into 10 to the power of minus 12 into 100, that is equal to 18 into 10 to the power of minus 10 coulombs.